So in the previous video, we talked about linear dependence and span. We just kind of went over some things that we have talked about previously here. Now, here what my goal is to show here is that given a set of vectors, S U1 through UN, right? And in there is some vector UT, right? And UT can be written as a linear combination of the other ones, right? In other words, what we're saying here is that this set S is linearly dependent, right? So what I'm going to set out here to do is that the span of S is going to be equivalent to the span of S minus the vector t that can be written as a linear combination of the other ones. Okay. Now, a couple things to look out for when given a set of vectors and you want to determine whether they are linearly dependent or not. Right now, if the vectors, let's say we're in the R to the M space, right? So vectors that have A1, A2, M entries, right? Now, if we have N vectors, to Vn, all right, now if N is greater than M, then automatically don't need to do any more work. The set is linearly dependent. All right, now the way you want to, why this must be true, all right, if we think of a matrix done in reduced row echelon form where I'm limited by the number of pivots to the number of rows that I have. Not that I'm always going to have exactly the number of rows pivots, but that is the maximum, right? So if we are dealing with R to the M at the nth row, right, I can have a pivot here. But I can't have more, right, because these stop. So if N is greater than M, that means we're going to have some free variables show up here. Okay, so right away that kind of gives us this idea of what to watch out for when given a set, and now I at least know what size it must be in order for it to be linearly dependent. Excuse me, linearly independent, right? So here, let's let V1 be 1, 2, 1, and then V2 be 3, 1, 0, V3 is equal to 0, 1, 4, and then V4 is equal to 4, 3, 1. All right. So again, I want to determine, is this linearly independent? Why or why not? So all right, so I want to determine if the non-trivial solution of something besides a trivial solution exists. Now, right away, right, we could see if we set up our matrix here that I know it's going to be linearly dependent. All right, so we're bounded here by the number of pivots here that can only happen in 3 rows. But since I have 4 vectors, right, then no, I'm guaranteed really that this set is linearly dependent. Okay, since 3 less than 4, set is linearly dependent. Okay, so not much work is done here, right? But what I do want to do is, well, can I write it in what vectors can I write as a linear combination of the other vectors in the set? So I'll start off by doing reduced row echelon form. That reduces to 1, 0, 0, 0, 1, 0, 0, 1, 1, 1, 0. So again, what this tells me here, we have these 3 pivots here, and then here, kind of back substituting, we see alpha 3 is 0 from that last row there. All right, I know alpha 4 is a dependent variable, free variable, we'll just call it t. Alpha 2 is negative t, alpha 1 is negative t. Okay, so going back to our linear combination here, negative t, we'll let t be 1, so we get negative v1 plus or minus v2. 0 v3, and then plus 1 v4. All right, equals to the 0 vector. So now we could see the existence of a non-trivial solution. So confirms what we thought, that it was a linearly dependent set here. And then more importantly here, if we kind of rearrange this, we have that v4 is equal to v1 plus v2. Okay, all right. So now, why does this not affect the span? All right, so now let's say that we have a set, our vector is v1, our set of vectors, excuse me, is v2, v3, v4. And I see that v4 is redundant in the sense that it's a linear combination of v1, v2. So that means that here, this set, v1, v2, v3, if I compare their spans, they are going to be the same. Okay, now why must that be the case? Well, let's say that some vector b is an element of the span of v1 through v4. Okay. All right. Well, that means that if it's in the span, there exists a linear combination alpha 2, 3v3 plus alpha 4 v4 equals to b. All right. So if it's in the span, there exists a solution, not necessarily unique, but a solution to this linear combination. Well, but I've already shown that v4 is just v1 plus v2. So we could say alpha 1 alpha 4 v4 is equal to b. Okay. All right. Actually, hold on. Excuse me here. I was out to replace v4 with v1 plus v2. All right, which I've shown up here, right? All right, and now rearranging this, we could say, all right, well, alpha 1 plus alpha 4, v1 plus alpha 2 plus alpha 4, v2, and then plus alpha 3, v3 is equal to b. All right, so now I'm able to write it as a linear combination of v1, v2, v3. So that means that b is an element of the span of v1, v2, v3. Okay, since B was just an arbitrary element here that I chose that was in the span, and now I show that it's in the span of the smaller set. Okay, all right, so we can remove vectors one at a time that are redundant, but in the next video we're going to look at a much more streamlined, much more effective way to get us to a linearly independent set from a linearly dependent set with the same span.